Okay, so please, as always, now that I've started the recording, please type your name into the chat so that we have a record of your attendance. Remember, anything that you type before I start the recording does not make it into the record. So when I look at the chat log after class, I only get things that have been typed after I start the recording. Okay. So, welcome everybody. I'm feeling much better this week. I think last week I was unwell, and everybody's been getting a little bit sick in the family, but I'm feeling much better this week. So I'm looking forward to class and to talking with all of you. Okay, so I guess just some announcements. Nothing really important to announce. We're still going to have class like regular for the next 3 weeks, and then there's going to be a short break before we finish things up, but I'll make that announcement later on. I think there may be some further progress on the certification for last year. So at the end of class, we'll talk to Abraham and we'll be able to talk a little bit about that to see if there's any updates for how that will work. And then also there's going to be this WITS mathematics competition, which is run by a friend of mine who lives in South Africa. So Liberia has participated the last 3 years, and it's a competition for high school students, and so they're going to participate again this year in Monrovia and in Ganta, and we'll get some further information about that. But that's going to take place. This is the so-called WITS mathematics competition, and it's going to take place May 5th through 11th. I mean, on one day during that week is when it takes place. Okay, so we'll hear more about that afterward. Okay. So today we're gonna continue our study of what we call this integral calculus. And we're not going to do any computations today that are very difficult. We're going to talk about ideas. And these ideas are going to be very important for next week when we're going to do an application to probability, which is one of the most important applications of calculus. So today we're just going to be establishing foundational material. But it's the reason that we're doing all of this is for next week when we're going to talk about what's called continuous probability. And continuous, I mean, most of you have seen maybe regular probability where you talk about flipping a coin or rolling a die. Um, Sorry, 1 second. 1 second. Sorry. All right. Sorry about that. Yes, so I was saying we're going to do this to study continuous probability. So a lot of probability that you've seen is probably what's called discrete probability, which is questions about flipping coins and drawing cards and rolling dice, where there's a discrete number of options that can happen. Continuous probability, which we're going to talk about next week, is when you have some uncertainty over something that can be continuous, like what is the temperature tomorrow? Or what is what's going to be, if I pick a random person, what's going to be their weight or their height? So these things vary over continuous intervals and vary over continuous intervals. And those we're going to need calculus to be able to understand, okay, to be able to analyze it. And the key thing that we're going to need in calculus is this thing called improper integrals that we're going to talk about today. Okay? So, but before we start talking about any of that today, I want to go over the homework and review some of what we've been doing because some people have missed some class or have come in late. So I want to make sure everybody understands what's going on. So what did we do last time? Well, we proved a few derivative formulas for some of these. Remember, these were called exponential and logarithmic functions. Okay. So the first formula that we had from last time was that the derivative of the function e to the x is just e to the x itself. So it's this interesting function whose derivative is itself. There are not a lot of functions that have this property. So e to the x is one of them. Then we also saw that if instead of e, you just have some number a, here a is a real number that's greater than 0, then the derivative of a to the x is a to the x times ln of a. Let's remember what this ln of a means. This means the log of a to base e. It's the so-called natural logarithm. Okay, so this is the thing that says ln of a means how many powers of e do you need to get a? So it's like, remember, ln of a is the solution to e to the x equals a. Okay, so it's the x that you need to solve that equation. That's what ln of a means. And then we also saw that the derivative of ln of x is 1 over x. Okay, and what that means is in reverse, that showed that ln of x is an antiderivative of 1 over x. So we had, remember, the power rule for antiderivatives, which is that antiderivative of x to the n is, well, we had two choices. We had 1 over n plus 1 times x to the n plus 1. This worked whenever n is not equal to negative 1. And then we have ln of x. That works exactly when n is equal to negative 1, right? Because we're saying when n equals negative 1, the antiderivative of x to the n, that means x to the negative 1, that means the antiderivative of 1 over x. And what we see from this equation here is that the antiderivative of 1 over x is ln of x. Okay, so we have this interesting dichotomy over here, meaning two different things that can happen, and the case n equals minus 1 just doesn't look like the other cases, right? Here we've got that the antiderivative of a polynomial here is just a polynomial where the exponent gets raised by 1, but over here, when you take the antiderivative of x to the minus 1, you get something totally different. You leave the realm of polynomials and rational functions, and instead you get natural logarithm. Okay, and this is one of the reasons why it's called natural logarithm, because it arises naturally when you're doing antiderivatives of a very simple function of 1 over x. Okay, and maybe I should just also recall what e is. That e over here is this number, which is about 2.718281828. It has 18281828, but it doesn't keep repeating. It just, it's an irrational number. It doesn't repeat forever, but it does have this repetition at the beginning. Okay, so e is this particular number here. It's between 2 and 3. Okay. Okay, so this is the summary of what we did last time. Okay, mostly we just got new formulas for taking derivatives of certain types of functions. Okay, questions about these formulas? Okay, so let's use these formulas to do some problems from the exercises. So the first homework exercise was to calculate the derivative of x times ln of x minus x. Okay, so we know we've got two parts here. The x ln of x, that's going to take some work over here. The minus x, that's pretty easy, right? That just goes to the derivative of minus x just goes to 1, right? So we have minus 1. And now here we need to figure out what's the derivative of x times ln.
Yeah, so
Yeah, Enoch?
yeah, yeah, like
Yeah.
yeah, and we know that if you have a function multiplied by another function like f of x times g of x, we will have to
Mhm.
use the Fourier rule
Right.
where you have here x to be f of x and
Yeah.
ln x is g of x. So we first day hold ln x and differentiate x, which will be 1 times ln x is just ln x. And we also hold x and differentiate ln x, which will be x times 1 over x. So if we have 1 over x, it will just be 1. And if we differentiate x alone
Right. So
on the
sorry,
side,
Enoch, let me just stop you. That's fine. I just want to be able to label this for everybody so that they're following. So this one here is when you differentiate f of x, the ln of x, you just leave g of x by itself. And here, this x over here is you just hold f of x. And here, this is what happens when you differentiate g of x, because we know the derivative of ln of x is g of x. Okay. All right. And then we have, minus one over here. Okay, continue, please. Enoch, you can continue. I just wanted to make sure that everybody was following. Yeah.
yeah, so now we know that if we multiply 1 by ln x, we will just have ln x. And
Hmm.
we multiply x by 1 over x, we will just have 1.
Great.
Then plus 1, yeah, we will have the 1 and the negative 1 going out. So the answer for the derivative of that entire function is just ln x, which is
Perfect.
also yeah, called the slope of the tangent line as well.
Great. So this is right. And so James has it in the chat also. So the derivative of this is ln of x. And it's just the product rule. Remember, it's a product f of x times g of x. And when we do the product rule, we do the derivative of one times pure the other one, and then plus the pure, the first one, times derivative of the second one, right? And so when you simplify this all, it comes out to be ln of x, which is really nice because this gives us a formula for the antiderivative of ln of x, right? We see the derivative of x ln of x minus x is ln of x, this natural logarithm. And so what that means in reverse, that the antiderivatives of ln of x are, well, it's exactly this function plus any constant, right? So they are x ln of x minus x plus c. Okay, so these are the antiderivatives. And the notation that we sometimes use for an antiderivative, which I haven't been using much, but I suppose I should do it, is it's the same integral sign. And if I write that the integral of ln of x dx, this just means when I don't have any limits here, this just means antiderivative. So I'm going to write this just means antiderivative. And so with this means this is x ln of x minus x plus c. Okay. So this antiderivative, maybe we don't know how to calculate it. So there is a way you can do it. You can use something called integration by parts, but we're not going to do that right now. But the point is, because you solve this example that the derivative of x ln x minus x is just ln of x, anytime you have a derivative formula, you always get an antiderivative formula in reverse. If the derivative of x ln x minus x is ln of x, then the antiderivative of ln of x is x ln of x minus x. And then you can, and that's what integration is exactly. And you can always add a plus c here because the constants don't matter. So this means antiderivative, and when you read it, you read it, and you call it integral. Read integral of ln of x dx. That's how you'd read it out loud. But when I have an integral sign like that, it just means an antiderivative. It's nothing fancy. It's just antiderivative. Okay? Okay, so you say integral, but you mean antiderivative. Okay, any questions about this example? Okay, great. So if this is fine, let's go to the next example. So the next example is calculate the derivative of x cubed plus 2x times e to the x at x equals 1, right? So here we now have a particular point where we're trying to do this. Okay, and the good news for this example is that we can use the same rule that we just used before, right? We use the product rule because it's a product of two functions. So this is f and this is g. It's a product of two functions. And so we can use, again, this same product rule to get it to work, right? So the derivative is f of x, or f prime of x times g of x plus f of x times g prime of x. But in the end, you're going to need to plug in
Yeah, sure.
x equals 1. Yeah, okay, Enoch, you want to do this one also?
Yep. I want to say something.
Sure.
Yeah. First, if we have this fund, we know that we have to find the derivative of the function
Mm-hmm.
where you, for example, if you have f of x plus g of x times h of x, which means the two functions are multiplied by another function out there.
Mm-hmm.
Yeah, which means, yeah, at first, if you let, you can differentiate f of x plus g of x, you hold or h of x constant, then
Mm-hmm.
you, yeah, so which means the entire two function inside here, we can differentiate them and
Mm-hmm.
hold e to the x constant, and also we differentiate e to the x and hold the entire function inside there. If we don't want to disobey e to the x throughout, it will also have a correct answer. Then it will finish, it will get a derivative in respect to x.
Mm-hmm.
Now we can plot in a value in a value of x to know the slope of the tangent
Mm-hmm.
line. Yes.
Exactly, right. So you can distribute this if you want, but there's actually no need to because you can just view it as a product the way it's written, right? So as you're saying, there's no point in distributing the e to the x first. You may as well just do the product rule with it the way it's written, and then you plug in 1 to find the correct slope of the tangent line at 1. Okay, so what do you get for this example?
Yeah, if you the first thing, okay, so the first thing is that if we can differentiate in respect using the product rule of f of x and g of x. So the
Hmm.
first thing, if we spread it out to be s q e to the x plus 2x
Oh,
e to
okay.
the
So
x.
you want to distribute it first. Okay, that's fine.
Yes,
Either way is
yes.
fine.
And
Okay.
we do it.
That's we can distribute it first. That's
Okay,
fine.
so let's distribute it.
Either way is fine. Okay,
Yes.
so we'll distribute it out. So x cubed e to the
Okay,
x.
s q e to the x
Yeah.
plus 2x e to the x.
Yeah.
Yeah, and we also have a note. And
Mhm.
yeah, I just want to say something.
Yep.
Yeah, I just want to say something to my comrades. The thing is that if you have the function to be just e to the x, and if the function in a power of x does not have any other function complicated, you just take e to the x at the derivative. But if e to the x, the x there is complicated, like for example, e to the power 2s squared, e to the power s squared, you will have to differentiate the power of the exponential function there, which is, for
Mhm.
example, if you have e to the 2x, you have to differentiate e to the 2x and just have e to the 2x, and also differentiate that 2x that in the power, which will just be 2. But
Yeah.
for
So
now,
we'll see this. We'll see this in some
yeah,
further
so for
exercises
now,
today.
yeah, but
Yeah.
for now, the power of e there is just x. So if
Mhm.
we are differentiating s q e to the x, we first hold e to the x constant and
Mhm.
differentiate s q, where we'll have 3s squared e to the x,
Yep.
3s squared e to the x. Uh, then we also hold s q constant and differentiate e to the x. We have plus, we
Mhm.
just have s q e to the x, the same thing.
Exactly, right. So if this is maybe I'll use the letters that you used. If let me instead of calling this F and G, I'll call this here this is f of x plus g of x, and this is
Time
going to be h of x. And
okay, okay.
so right, so then this over here is going to be f of x times h of x, and
And g
here
of
is
x and
going
h
to
of
be g of x times h of x. Great. And so this
okay.
here is f prime of x times h of x, and then this here is f of x times h prime of x, which is just the same thing as h of x because it's e to the x.
Yeah.
So wonderful.
So
Okay, so keep going.
yeah, so we do plus, and we have two functions again, where we have 2x is another function g of x, and e to the x is the same h of x. So first we differentiate g of x again, and whole h of x, which will be, if we differentiate 2x, we just have 2
Hmm.
times e to the x.
Great.
And we do plus again, we differentiate e to the x, and whole 2x constant, we will have plus 2x e to the x.
Perfect.
Yes, and now we know that in this function we have e to the x in common to all. Yeah,
Okay.
we have h of x in common to all. So we, if we let, we factor out h of x, which is e to the x. So if
Hmm.
we factor out e to the x, we'll have, okay, we'll have 3x squared plus s cubed plus 2 plus 2x, all multiplied by e to the x.
Perfect.
So
Okay.
now,
Yeah.
yeah, so that's it. And we know that those functions in there, none of them are similar. So we don't add them, we just maintain them like that. And we put in our value of x at x equal 1. We put 1. Okay, so by plotting the value of
Hmm.
x equal 1. Yeah, so we have 3 times 1 square plus 1 cube plus 2 plus 2 times 1. So 1 square we know is just 1. 1 times 3 is 3 plus 1 cube will just times e to the 1. So e to the 1. Yeah, so we
Hmm.
just put in the value times e to the 1 power, which should just be e. Okay. So we just add our values.
Hmm.
We just add the value, we get 2 plus 1, we get 4. So the entire value here, it will be 8.
Hmm.
So the complete answer for this function will be 8e to 8e.
Perfect.
Yeah, so
Okay.
if you like also, you can put in the value of e, which will be 2.718, and just multiply. But if you like, this is the best way to express it for this one.
Right. It's probably easiest to just leave it like 8e. If you want to expand it out, you can do that, and that will give you something like about 23 and a half to 20, 21 and a half, something like that. Maybe a little bit more than 21 and a half. But for us, 8e is a good enough answer over here. All right. So this is very clearly explained, and I've tried to write the actual steps of solving the problem are all in blue, but I'm trying to write in the red what everything means, why everything shows up. So if you're looking back at your notes, the point is you distribute, you get f times h plus g times h, and then you're applying the product rule to f times h. That gives you all these forms. And then you apply the product rule to g times h. That gives you all of these forms. And then when you collect and simplify and plug in x equals 1 to evaluate everything, you end up with 8e over here. Okay? All right. Any questions about this one? Okay. And I should say also, if you don't want to distribute it all out, it's
Yes, sir.
fine to
Yes, sir.
just do the product rule
Yes, sir.
directly, sorry, with x cubed plus 2x times e to
Hello.
the x. And you just
Hello there.
take this times the derivative of this
Hey, Spring, you
plus
getting me
the
clear?
derivative of this times this. Yes, sorry. Comment. Comment? No? Okay. Okay, so I think that's good enough for this question, okay? And hopefully the way the notes are here, if you forget how it works, you can go back and look at it and it will make some more sense, right? Maybe I should just say for the future notes, what we're doing here is using the product rule. Okay, great. Okay, so I want to do one more thing from last time. So one of the big applications of anti-differentiation that we saw is it allows us to determine the area under a curve. And specifically, if we look at the graph of y equals f of x between two x values, x equals a and x equals b.
Hello there.
Yes, sorry, question?
Are you getting me?
Yeah, Prince, do you want to go back here? Prince? Uh, now I'm not getting you anymore. No, sorry, I don't hear anything.
Yeah,
Yeah,
yeah. I
yeah,
have a, yeah,
Prince.
yeah, yeah. You getting me now?
Yeah, getting you now.
Okay. Ah,
Hello, boss.
Yes, James.
Yeah, so like my colleague said that you have to just obedient to use the product rule for leaving it as the parenthesis as f or x and the next parenthesis or e or f to be g or x. Can you still use the product rule in that setting that you're gonna work?
Yes, yes, you can. Maybe, maybe I'll do that. Let me just do the question with the other method. We'll see that we get the same answer, right? So if we have x cubed plus 2x e to the x, if I call this f of x and this g of x, then by the product rule, we're going to get we get f of x, so x cubed plus 2x times the derivative of g of x, which is e to the x. So this would be f of x times g prime of x. And then similarly, we get the derivative of f, that will be 3x squared plus 2. That would be f prime of x. And then times g of x, which is just going to be e to the x again. Okay, and now if you want to combine them, that's fine. You get x cubed plus 2x plus 3x squared plus 2 times e to the x. And if you look, this is the same as before, right? X cubed plus 2x plus 3x squared plus 2 e to the x. And here we had exactly the same thing. It's written in a different order, but it's the same thing. It's x cubed plus 2x plus 3x squared plus 2. It's all of the exact same terms. Okay, so it works the same regardless of which way you do it. And then if you plugging in
Say
x
plug in.
equals 1, we get exactly 1 plus 2 plus 3 plus 2 times e to the 1, and this simplifies to the same answer, which is 80. Okay. Um, great, yeah. So you can do it either way and you get the same answer. Both ways are fine. Okay, other questions? And it's not clear to me that one way is easier than the other. It's a matter of taste, whatever you prefer.
Yeah. That boss?
Yes.
So like now my colleague also saying that if like the derivative of e of x is just like say you say the derivative of e of x is e of x,
Mm-hmm.
right?
Yep.
So if e of x was when x was another function like x squared, x cubed, will it be the same e of x?
No, it's not. And we'll see an example later today where it's not the same. Yeah, so we'll see an example later on today. So maybe I don't want to talk about that right now. We'll discuss that when we see the next example. Okay, for this example, you only need to know e to the x as it is. Okay, so what we're saying is that these antiderivatives allow us to find the area under a graph. So it's f of b minus f of a, where this capital F is an antiderivative of little f, which is making your graph. And so this result is called the fundamental theorem of calculus. And in terms of notation, the way you write it is if you write the integral from a to b of f of x dx, that means find an antiderivative, capital F of little f, evaluate it at b, evaluate it at a, and then subtract. That's this f of b minus f of a. And what this is this is exactly giving you, the area under y equals f of x between x equals a and x equals b. Okay, so we can evaluate this area by using antiderivatives. And so in particular, we have this example that we did last time. If we're looking at the area under the graph of 1 over x between 1 and just some number b, well, we have to take an antiderivative of 1 over x. We know that the antiderivative there is going to be ln of x, because the derivative of ln of x is 1 over x. And so we have to do ln of the top limit, so ln of b minus ln of 1, but this ln of 1 is just 0, right? Because it's a logarithm of 1, which means it's saying, what do you raise e to in order to get 1? Well, right? Oh, oopsie, didn't mean to do that. Sorry. Well, ln of 1 equals 0 because e to the 0 is equal to 1. Saying, what do you have to raise e to in order to get 1? The answer is you have to raise it to the 0th power. So you get ln of b minus ln of 1, and that's equal to just ln of b. Okay, so another way of saying this is that the area under the graph of 1 over x from x equals 1 to x equals b, that area is exactly ln of b. Okay, and that's what comes from this formula over here. So this is what sets up the next homework question. So the next homework question says, give an interpretation of the number e squared in terms of the area under the graph of 1 over x, right? So if I draw this graph, y equals 1 over x, that's what the graph looks like, at least the part in the first quadrant. That's what this graph looks like. And I want to understand, what can I say about the number e squared? Maybe I'll put it here. This is e squared. It's, it's a little bit, it's equal to 7 point some stuff. And so the question is, what does e squared have to do with this graph? Well, what happens if I start the graph at 1 over here, and I look at the area under the curve between x equals 1 and x equals e squared? Well, from the previous page, we have that the area equals, well, it says the area between 1 and e squared under 1 over x is just going to be ln of e squared minus ln of 1. Right? So this area over here is going to be, well, by definition, it's the integral from 1 to e squared of 1 over x dx. And that we've seen from the previous page is the same thing as ln of e squared minus ln of 1. And well, ln of 1 is just 0, so that's just ln of e squared. And what is the natural log of e squared? What power do you have to raise e to in order to get e squared?
So, Andrew, I want to ask.
Question, yes. James.
So, that the number e squared represents the x value?
Right. If I put it as an x value over here, then we're saying the area under this graph between x equals 1 and x equals e squared. I want to calculate that area.
Okay.
And what the formula says is that area is going to be the natural logarithm of e squared. So I want to know, does this simplify? Can we get a simpler expression for a natural logarithm of e squared? Well, remember what natural logarithm means, right? Natural logarithm is basically saying we're trying to solve the equation. We're trying to solve, we're trying to solve the equation e to some power is equal to e squared. So how do we solve this for x? What's the solution here? You can kind of just read it off. What power of e is equal to e squared?
X.
Right. So what is the solution for x in this equation? What should x be equal to in order to make this equation true?
2.
2, exactly, right? So that's saying that the natural log of e squared is equal to 2, right? Because natural log of e squared just means how do we solve the equation e to the x equals e squared, right? So this 2 over here is the solution to this equation. That's what it means to take a natural log. So the natural logarithm of any power of e is that power. So ln of e cubed is 3. ln of e to the fourth is 4. ln of e to the 100 is 100, right? No matter what the power of e is, you can think of ln as the inverse function of e to the x. So the ln and the e to the x cancel each other out, and you're left with just the 2. Okay? So what that tells us is that if we look under this graph of y equals 1 over x, and we look between x equals 1 and x equals e squared, this area here is actually equal to 2. Okay, so that's kind of interesting, right? You go from 1 to 2.7 squared, this number that's about 7.3. And if you look under the graph between 1 and e squared, then the area that you get here is equal to exactly 2. Okay, so that's a way to interpret the number e squared. It's the place where you have to draw this line in order to get an area of 2. All right, any questions on this?
Yeah.
Sorry.
Hello there.
Hello. Yeah, question? Prince?
Yes, Prince.
Yeah.
Getting me now?
Sorry, not getting you. I'm losing you. Do you want to type a question in the chat? Because it seems like the connection is bad. You're getting okay, yeah. I'm not getting you, Prince. Hello?
Wow.
Sorry, hello? Okay, so I'm not going to be able to hear you. So if you have a question, you'll need to type it in because I'm not getting you. Okay, I'm going to move on. Okay. Oh, what happens if e is raised to the fractional part? Exactly the same thing, right? So I'll add another page, right? So exactly the same thing. So if I want to take ln of e to the 2.317, this is exactly equal to 2.317, right? You raise e to any number at all. If you take ln of that, then that undoes the e. Okay? Because this is saying, what power do you need to raise e to get e to the 2.317? And the answer is 2.317. The answer doesn't change. Same thing here. ln of e to the 1 half is equal to 1 half, right? No question at all. Okay, so it's the same thing. No matter what number you put here in the exponent, it can be a negative number. That's fine too. ln of e to the minus 4 is equal to minus 4, right? Whatever your exponent is, that's always what shows up when you take the natural logarithm. Okay, any real number at all. Okay. Okay, so hopefully that answers the question. I'm going to move on. Okay, so here's a first example of an improper integral. What is the area under the graph of y equals 1 over x to the right of x equals 1? Okay, so let me draw the picture again. This graph looks like this. Here's x equals 1. And now I'm asking, this is the graph of y equals 1 over x. And now I'm asking for the entire area to the right. Now notice this has an asymptote. This has a horizontal asymptote on the x-axis, right? So this graph is the graph of 1 over x. The limit is going to be 0. But this area does go on forever in this right direction. So what we have to do is we're trying to figure out this total area. So the area, the way we should think about it is, let's say that I have some point B here. We know that the area between 1 and B is, we called it this integral from 1 to b of 1 over x dx. And this we already saw was equal to ln of b minus ln of 1. And that was the same thing as just ln of b. So the area between x equals 1 and x equals b is ln of b. So if we want to figure out the entire area to the right, what we're really doing is we have to take the limit as b goes to infinity, right? Because we want all of this area to the right. So we don't want to cut it off at b. We want everything, so we have to take the limit as b goes to infinity, right? So we have, so total area to the right of x equals 1 is the limit as b goes to infinity of this expression. So it's the limit as b goes to infinity of ln of b. And it turns out, what is the limit of ln of b as b goes to infinity? Well, it turns out that this limit is also infinity. Okay. And the reason is, we can do this maybe with a table of values, right? I'll do a table of values. So I'm going to have b and I'm going to have ln of b. So if b is e to the 10, then ln of b is 10. If b is e to the 100, then ln of b is 100. If b is e to the 1000, then ln of b is 1000. If b is e to the 10,000, then ln of b is 10,000, and so on, right? And so you can see as b gets higher and higher, maybe if you take it with higher and higher powers of e, then ln of b is also getting higher and higher. And there's no bound, right? This can go off to infinity. I can do e to the 1 million, e to the 1 billion, e to the 1 trillion. This is going off to infinity, right? So what this shows for us is that as your b goes off to infinity, that ln of b also goes off to infinity. Okay? So this is telling you that the limit as b goes to infinity of ln of b is infinity. And what that means in terms of this graph is, we're saying as b goes to infinity, the area gets bigger and bigger without end. So the upshot of this is that the area to the right, of x equals 1 is infinite. Okay? Because if we cut it off at b, that area would be ln of b. But if we want the total area, we have to take the limit as b goes to infinity. And it turns out the limit as b goes to infinity of this is actually infinity. Okay, so that means if you're going to take the total area all the way to the right without bounding it at all, you're going to get infinite area, which is maybe not that surprising because this is an infinite shape, right? I mean, this is an asymptote, which means it never actually hits the axis. So this area does go on forever. And it turns out that it's actually equal to infinity. All right, any questions on this example? It's a fairly important example. Okay. So this area is infinite. Okay, because ln of b is infinite as b goes to infinity. Okay. What about, let me do a similar example. So same question, but now instead of the graph of 1 over x, we're going to have the graph of 1 over x squared. Oh, by the way, I should say all of this material, let me give you a textbook reference. All of this material is in chapter 6.6. So this is all, this new material is in chapter 6.6 of the book. Okay. Okay. So what is the area? Now, same question, but we're going to have the graph of 1 over x squared. Okay, this graph more or less looks the same. Okay, this is going to be y equals 1 over x squared. So we have the same thing. We have 1. Going to look at x equals 1, and we're looking at the area to the right of it. Okay? And we again have an asymptote, right? Because the limit as x goes to infinity of 1 over x squared is equal to 0. So this again has the same asymptote going to 0. But notice that if x is really big, then 1 over x squared is a little smaller than 1 over x because you're dividing by the square of x instead of just by x. So let's figure out this area the same way. I'm going to imagine some point B here where I'm going to end this, right? And so the area between x equals 1 and x equals b is going to be the integral from 1 to b of 1 over x squared dx. Or another way of writing that is the integral from 1 to b of x to the minus 2 dx. Okay, right? 1 over x squared is the same as x to the minus 2. Now this is a standard antiderivative that we can evaluate using the power rule. This doesn't require logarithms or anything. It's just the power rule. We raise the exponent by 1, and we put that in the denominator. So the antiderivative of x to the minus 2 is going to be x to the minus 1 times 1 over minus 1. And remember, we had this notation from last time. I draw a bar, and I write the 1 and the b. That just means evaluate this at x equals b, and evaluate this at x equals 1, and take the difference. So this over here, I'm just going to simplify it. 1 over minus 1 is just minus 1. So this is just minus x to the minus 1, 1 to b. And what's x to the minus 1? That's just 1 over x. So that's the same thing as minus 1 over x from 1 to b. Right. So James, that answer is correct. So let's do this. What do we have? I punch in b, so that's negative 1 over b minus, now I punch in 1, is negative 1 over 1. Right? I punch in the b here, and then I punch in the 1 here. And if I simplify this all, the minus there's become pluses. And so I end up getting 1 over 1 minus 1 over b, or in other words, 1 minus 1 over b. Okay? So the area between x equals 1 and x equals b is 1 minus 1 over b. Right? So is that okay so far?
That helps?
Yes, James.
Yeah, like the first rules where you have y is equal to 1 over x, we'll have to use the Ln function to find it because when x goes up, it turns to minus 1. If you use the power rule, it goes to 0. So now 1 over x squared. Can you still use the Ln to say Ln as if I
No,
know x
you
squared?
cannot. You cannot use the ln for this, right? Because remember, this is the power rule, right? This is x to the minus 2. So we have our power rule over here, right? This is the power rule. So the power rule says, how do you do an antiderivative of x to the n? And the point is, it involves an ln only when n is minus 1. So it's only if you have x to the minus 1, which is 1 over x. That gives you ln of x. If you have x to any other power at all, the antiderivative is just going to still be a power, right? You just raise the power by 1 and divide by that power. So in our example, n was equal to negative 2, right? It's x to the negative 2, so you're not going to use logarithms. You're going to use this first part of the rule instead. Because n is going to be -2. So you're not going to use the logarithms, you're just going to use this part of the rule. Okay? So if we go
Thank you.
back to our example, right? So for x to the -2, it just becomes x to the -1. You raise the exponent by 1, and then you divide out by the new exponent. And so with this formula, it does not have a logarithm anywhere. And so when you evaluate this at b, you get -1 over b, and you evaluate it at 1, you just get -1. And then when you subtract them and simplify, it comes out to be 1 minus 1 over b.
That all right?
Yes, James.
So like finding the area under the curve. So the shape of the area left, for example, if you find the area, maybe you have the area under the curve is kind of on a trapezoid form or maybe a triangle. The formula doesn't matter. We just use the upper bound and the lower bound of integration.
Right. Yeah. The shape doesn't matter for the integration, right? I mean, this is some curved shape, right? It's not a standard geometric shape. So it's not going to be, there's not really going to be any way to evaluate it other than doing the integration. And this b we just wrote down. The whole point is to get the entire area, we're going to have to take the limit as b goes to infinity, right? That's how we get the entire area to the right, because this b is going to be moving over to the right. So if we take the limit as b goes to infinity of this expression, 1 minus 1 over b, well, what do we get here? Well, James already has the answer, right? As b goes to infinity, the 1 over b goes to 0. And so what we're left with here is just the 1. So this limit is equal to 1 minus 0, which is just equal to 1. So this is kind of unusual, right? You have an area that goes on forever. Remember, this has an asymptote. It does not ever hit the x-axis. It goes on forever. It gets very skinny, but this area under the curve goes on forever. But even so, the area is finite. So even though the shape goes on forever, the area is equal to just 1. Unlike in our previous example, where the area was actually infinite. So under 1 over x, the area is infinite and it goes on forever. For 1 over x squared, the area is only 1, even though it goes on forever. Okay, so it just shows that area is not quite as intuitive a concept as we think, right? Somehow this gets squeezed together so fast that it only accumulates finitely much area. Whereas when you have 1 over x, which is a little bit higher than 1 over x squared, it kind of looks like this, then you've got more area, and in fact, you have so much more area that it ends up being infinite instead of just being 1. Okay, so this is an important idea that you can have two different shapes that both go on forever, but one of them has finite area and the other one has infinite area. Okay, and we see this with these two examples here. Okay, so any questions on this example, why we get 1 here instead of infinity? Okay, so let me say what's the general principle. So the general principle, this is called a type 1 improper integral. So what we actually do is when we want to look at the entire area to the right of some real number a, we write it using this notation. We say the integral from a to infinity of f of x dx. This means, the area under the graph of f of x to the right of x equals a, right? So we don't just go from a to b, we don't stop it at some b, but we go on forever to the right. So that's what we say, a to infinity. And what does this notation actually mean? It means we take the integral from a to b, we look at what the area is going to be like between A and B, but then we take the limit as B goes to infinity, right? This is exactly what we did in these previous examples. We do the integral from A to B in the previous examples, A was equal to 1. So we take the integral from A to B, and then we let B go to infinity. And if the limit exists, we say that the improper integral converges to the limit. And if the limit doesn't exist, then we say that the improper integral diverges. So in our case, we have that the integral from 1 to infinity of 1 over x dx diverges, right? We saw this because it goes to infinity, but the integral from 1 to infinity of 1 over x squared dx converges to 1. Okay? And that converges to 1. Okay, so this is the contrast of these two examples that we've seen, right? One of them went to infinity, so we say that it diverges, and then the other one is, actually converges to a number. It actually converges to 1. Okay. All right, so any questions on kind of the distinction here? So we've got integrals that go off to infinity, and what they really are limits. It's really you take a standard integral where you're doing an antiderivative and evaluating it at two numbers, but after you do that, you then let one of your limits go off to infinity. And that, instead of giving you the area between A and B, it gives you the area from A all the way out. Okay. All right, let's look at another example. So we know that the derivative of e to the x is e to the x. We've seen this. So this is a question that people asked. What is the derivative of e? Now you have something here in the exponent. What is the derivative of e to the minus x? And then after that, I'm going to ask you what's an antiderivative of e to the minus x. So let's recall that if we do the derivative of e to some function, let's call it g of x, that this is equal to, well, it starts just like with e to the x. It's just g to the e to the g of x itself, but then you have to multiply it by the derivative of g. Okay, this comes from the chain rule. I'm not going to rederive it, but this is a formula that if you have e raised to some function, then the derivative is e raised to that same function times the derivative of that function. This came from the chain rule, right? So if we're taking the derivative of e to the minus x, what's that going to be here? What do we get when we evaluate this at e to the minus x? Anyone?
Is that the chain rule you use?
Yeah, I mean, the chain rule is how you derive this formula. Okay, so I derived it last week using the chain rule. The idea is you're raising e to the some other function. And so from the chain rule, you have to take the derivative evaluated at this other function. That's the e to the g of x. And then you have to multiply it by the derivative of the inside function. That's this g prime of x over here. Okay, so maybe I should say that that isn't the chain rule, but it follows from the chain rule.
All right.
Okay. So now, if our g of x is minus x, if this is our g of x, let's just look at the formula. What are we going to get? We get exactly negative e to the minus x. Perfect, right? We get e to the g of x, so that's e to the minus x, and then times the derivative of negative x, right? So the derivative of negative x is negative 1. Right? Or in other words, negative e to the negative x. Okay. Okay, so the derivative of e to the negative x is negative e to the negative x. So in particular, that tells you that an antiderivative of negative e to the negative x is e to the negative x. So let's say I just want the antiderivative of e to the negative x instead of negative e to the negative x. If I just want the antiderivative of e to the negative x, can anybody guess what that is? What's going to be an antiderivative of e to the negative x? We know that antiderivative of negative e to the negative x is e to the negative x.
One.
And what about,
This one.
yeah. Yes, James?
One.
No, not quite 1. No, the antiderivative can't be 1 because the derivative of 1 is 0. Oh, I mean, the answer to the problem might be 1, but we're nowhere near being able to do that yet. So,
Oh,
right, first we need to figure out what is an antiderivative of e to the minus x. Right, this is the first problem before we're going to evaluate this integral. Okay. Well, the point is, you want to know something whose derivative will be e to the minus x. Well, your first guess
hello.
might be, yes, hello?
Are you asking for the antiderivative?
Yeah, the antiderivative of e to the minus x.
Is minus e
Mm-hmm.
raised to the minus x plus c, which is the
Perfect.
constant.
Perfect. Right? The point is that if the derivative of e to the minus x is minus e to the minus x, then the derivative of minus e to the minus x is going to be minus e to the minus x, which is just e to the minus x, right? So e to the minus x gives you minus e to the minus x. That means minus e to the minus x will just give you regular e to the minus x. Okay, so an antiderivative of e to the minus x is actually going to be minus e to the minus x plus c. Okay, so we can guess that from knowing that the antiderivative of minus e to the minus x is e to the minus x. So if you want to change this negative sign in the function, you also change it in the antiderivative. So you throw on an extra minus sign there. Okay. So this is the first part of the question. So an antiderivative of e to the minus x is minus e to the minus x plus c. So now to evaluate this, remember what this means. This, by definition, is the limit as b goes to infinity of the integral from 0 to b of e to the minus x dx. Right? This is what this means by definition. Why is the derivative run from infinity to 1? Well, we haven't answered the question. This up here has nothing to do with infinity. Here, I'm just asking what's an antiderivative of e to the minus x. That has nothing to do with the limits on this integral. This is just the first part of the question, that the antiderivative of e to the minus x is minus e to the minus x plus c. Okay? So now let's use this. Sorry, 1 second. 1 second. 1 second. Sorry. Oh, okay.
Hello, Andrew.
Okay, great. Sorry about that. Yes. Um, so so we're doing the integral from 0 to b of e to the minus x dx. And what we've evaluated in the first part is we showed what an antiderivative is. And the c doesn't matter. You can ignore the c when you're doing one of these evaluations. So it's just minus e to the minus x. So this is going to give us minus e to the minus, well, sorry, let me say limit as b goes to infinity. It's going to give us minus e to the minus x, and we're going to evaluate it between 0 and b. That's this notation. May not be dark enough also from where it Okay, good. All right, so what is this? This is equal to minus e to the minus b minus e to the minus 0, right? So there's a lot of there's a lot of minus signs here, but we just have to evaluate this carefully. We know these two minuses become pluses, and so this becomes minus e to the minus b, and then plus e to the minus 0. But e to the minus 0 is just e to the 0, which is 1. So this just becomes 1 minus e to the minus b, right? And this is all limit as b goes to infinity. Okay. So now we have to evaluate the limit as b goes to infinity of 1 minus e to the minus b. And maybe let me just rewrite this as the limit as b goes to infinity. Well, e to the minus b is the same as 1 over e to the b. So Isaac, I'll answer your question in a second. And so now what do we have here? Well, if we let b go to infinity, that means this denominator here is getting really, really, really big, which means 1 over the denominator is getting very small. It's going to 0. So this goes to 0 as b goes to infinity. And what you're left with as a final answer is, again, 1. Okay, so this integral from 0 to infinity actually gives you 1 as an answer. So Isaac asked, what's the differences between derivative and antiderivative? Well, they're just two different things. It's kind of, you should think of them as like, what's the difference between addition and subtraction? Or what's the difference between multiplication and division? Or what's the difference between squaring and taking a square root, right? They're processes that undo each other. So the derivative is just the derivative. You take a derivative. An antiderivative means you're asking which function has that function as a derivative. Now, in this particular example, the derivative and the antiderivative are the same. If you have e to the minus x, then the derivative is minus e to the minus x, and the antiderivative is also minus e to the minus x. But that is a very, very, very specific coincidence. That is not the general thing that happens. Usually, if you have something like x squared, the derivative would be 2x, but the antiderivative would be 1/3 x cubed. So, completely different. Okay, so you should think of them as processes that reverse each other. Okay. So in this case, when we evaluate this integral, you end up getting 1. Okay, and you have to figure out this antiderivative, which is the first part, and then you have to actually plug in b and plug in 0 and keep careful track of your minus signs, and then you need to be able to evaluate this limit as b goes to infinity of this e to the minus b. But the way you evaluate that limit is you write it as 1 over e to the b, and you see that the denominator goes to infinity, which means the fraction is going to go to 0. So what you end up being left with is just the 1 over here. All right, any questions on this one? Okay. All right, so let's look at another example. So this one I'm going to do. So we may not finish all of the examples today. That's fine. So let's calculate the derivative of negative x times e to the negative x minus e to the negative x. Okay? Okay. Okay. One second. Okay, so let's just calculate this derivative. We're going to start here with a product rule, right? So if we call this negative x is going to be f of x, and this e to the negative x is going to be g of x, Let's do our product rule the way that we did it before. So we're going to have f of x, so negative x times the derivative of g of x. Well, we already did this. The derivative of e to the negative x, we already did on the previous slide. That was going to be negative e to the negative x. And then plus f prime of x, which is going to be minus 1, times g of x, which is going to be e to the negative x. So this here, remember, this is f of x, this is g prime of x, this is f prime of x, and this is g of x. Okay. And now we subtract this e to the negative x, which we already calculated the derivative of. That was negative e to the negative x. Okay. So let's simplify this. Well, this becomes a plus and a plus. So we end up getting, and this becomes a plus and a plus also. A plus and a plus here. So what we end up getting is, oh no, sorry, never mind. Sorry, this is a plus and this is a plus. So this ends up simplifying to x e to the negative x minus e to the negative x plus e to the negative x, right? This is minus e to the negative x, and this is plus e to the negative x. So these two cancel out, and we're left with just x e to the negative x. Okay, so that's the answer here. Okay. Okay. So now that so this is the derivative. So now we're asked evaluate this integral, 0 to
Yes.
infinity of x e to the negative x dx. Yes, Enoch?
Yeah. Yeah. Actually, I'm not talking because I'm doing something else here. But this one now you have the antiderivative of x e to the negative x, which is the product of two different functions, like f of x and g of x. In my view, in the other side, I prefer we use the formula where say that you have v du, or you have uv minus the integral of v du. So
Yeah, so
we can let u to be equal to x. It will let u to be equal to e to the negative x and differentiate both sides.
okay, yes. So there's a formula, there's a general, procedure called integration by parts that lets us figure out this antiderivative. I don't want to teach that because, at least not now, because that would take the entire class. So for this example, we can just use the fact that from this first part of the exercise, we know what an antiderivative for x e to the minus x is because we calculated this. We know that the derivative of this function equals x e to the minus x. So maybe I should just, what does that mean? This means that negative x e to the minus x minus e to the minus x is an antiderivative of x e to the minus x, right? So there is now, how would we ever figure that out? The answer is exactly what Enoch says. There's something called integration by parts that if you want to read about it in the book, you can. It is done in chapter 6.1 in the book, if you want to read this. But that would take us too far afield and would take the rest of the class to talk about how to do. So for now, for this example, let's just use that you did this calculation already. So you already calculated this derivative. You got x e to the minus x. Okay, so what do we have to do? We just do the same thing, right? So this definite integral, right? We do, as usual, the limit as b goes to infinity of the integral from 0 to b of x e to the minus x dx. Now, we know how to do an antiderivative here, right? So the antiderivative is exactly given by this function over here. So what are we going to do? This is going to be the limit as b goes to infinity by, let's just take the antiderivative. So that's x e to the, sorry, negative x e to the minus x minus e to the minus x. And we're going to evaluate that from 0 to b. So this is what? This is the limit as b goes to infinity. Well, first I'm going to plug in b. So I get negative b e to the minus b minus e to the minus b. And then I have 0. So I have minus negative 0 e to the minus 0 minus e to the minus 0. So let me simplify this a little bit. Well, this has a 0, so this is 0. This is minus e to the minus 0, so this is minus 1. And we have a negative 0 minus 1. So this is equal to the limit as b goes to infinity of negative b e to the negative b minus e to the negative b. And then we're going to have a plus and a plus 1. So this is going to end up giving us plus 1. Okay? And now maybe simplify this one more time. This is the limit as b goes to infinity. I'm going to write it like this. Negative b divided by e to the b minus 1 divided by e to the b plus 1. Right? Because the e to the negative b, instead of writing it as multiply by e to the negative b, I can always do dividing by e to the b. That's the same thing. So I have negative b divided by e to the b, and here I have minus 1 divided by e to the b plus 1. Okay. Okay. So let's do this limit. So how do we do this limit? Well, this part, we can do each of the three limits together. I mean, each of the three limits separately. So we have the limit as b goes to infinity of negative b over e to the b, minus the limit as b goes to infinity of 1 over e to the b, and then plus the limit as b goes to infinity of 1. Well, this part's just equal to 1. The 1 stays as 1. Limit as b goes to infinity of 1 over e to the b, we've already seen this. We did this in the last problem, right? You're getting 1 over e to the infinity. That's going to be equal to just 0, right? Because the denominator is blowing up. And now here you have this interesting case, right? Because what happens when b goes to infinity? Well, the numerator goes to infinity, but the denominator also goes to infinity. So this is one of these infinity over infinity. It's one of these indeterminate forms, right? So we have a rule for how we evaluate a limit like this. Does anybody remember what rule we use to do this limit? Well, remember, when you have an indeterminate form like infinity over infinity, you can use L'Hospital's rule to evaluate it. That means you take the derivative of the numerator and you take the derivative of the denominator, and now you evaluate this new limit. So the derivative of the numerator is just minus 1. And the derivative of the denominator, well, the derivative of e to the b is just e to the b. So we have e to the b. This is L'Hospital's rule. So you take the derivative of both of these, and now this is no longer indeterminate, right? Because you've got a minus 1 in the numerator, but an e to the b in the denominator, and that's going off to infinity, right? So this limit over here is equal to 0. So what you get then for your final answer is we did all of these limits, so we're going to get 0 minus 0 plus 1, and that's equal to 1. Okay. So you get one, just as James said in the comments, but there's a long way to go before you get one. You can't just look at this and say the answer is one. There's a lot of steps, right? You have to know what the antiderivative is. That's from this part one over here. Then you have to evaluate this expression, which has a lot of minus signs that cancel each other out. And then you need to take a limit. And maybe this limit and this limit are straightforward, but you end up getting another one of these limits with an indeterminate form. That means that you have to use L'Hopital's rule in order to do it. Okay? So in order to come up with this final answer of 1, and that's telling you that the area under the graph of x e to the minus x between 0 and infinity is equal to 1, in order to come up with that answer, you have to really, do a lot of algebra and calculus in order to get there. And so maybe I should show you this graph. Let me just graph this on Desmos so that you can see the graph. So let me share my screen here. Let me share. So let me share here. If I just want to draw the graph, what does this function look like? So y equals x times e to the minus x. What do we have? Well, I'm going to zoom in a little bit. So it kind of looks like this, right? So it's, of course, at x equals 0, you have y equals 0 because it's x times e to the minus x. So you plug in x equals 0, you get 0. And then it looks like this function gets positive, positive, positive. But then as x goes off to infinity, the e to the minus x shrinks to 0 much faster than the x grows. And so you end up with this function having an asymptote at 0. Over here, it looks like it's basically going to 0. And so what this integral is saying is that if you take the entire area under this curve here, including this teeny tiny little thin sliver over here, that total area comes out to be exactly 1. And if you look at this, this makes sense, right? Each of these squares is a half unit square. So that means it has an area of 1/4 unit. So an area of 1 is about 4 of these big squares because they're each a half unit by a half unit. So you can see that already you're getting almost 4 of these big squares, maybe in the first few boxes under the graph. And then everything else that you have ends up giving you a total of 4 squares. It gives you this total area of 1, which is the same as 4 of these large squares. Okay, so it's good to look at the graph and see what's actually going on here. Okay, so let me go back to Zoom. Let me go back to the meeting. Let me end my share. How do I do the stop share? If I stop share, can this start sharing again? Let me share again. Okay, good. So, okay, so that's what, so this integral comes out to 1, and it's not just a bunch of meaningless algebra. This has a geometric meaning. It shows you that the area under that curve is actually equal to 1. Okay? Okay. Questions on this example? Okay, so let's move on. Okay, so here's another type of improper integral. So let me ask you a different question. What is the area under the graph of y equals 1 over x between x equals 0 and x equals 1? So I'm going to draw the same graph, and I'm still going to have 1, but now what I'm really looking for is this whole area to the left of 1. And remember, this graph y equals 1 over x has a vertical asymptote at x equals 0, right? It goes off to infinity as x goes down to 0, right? Because the denominator goes to 0. So now I want to know what's this total area over here. Okay? And the idea is, well, I would like to do the area, let me write over here, maybe I'll call this A, is that the area between x equals A and x equals 1 is the integral from A to 1 of 1 over x dx, right? That would be if I just wanted the area between some x value A and 1, the integral from A to 1 of 1 over x dx. And that's equal to, we know the antiderivative of 1 over x is ln of x going from A to 1.
Yeah, so yeah,
Yes.
that's it.
Yeah.
Yeah, the R function is in the form, for example, where you have the once you have the derivative of the function
Mm-hmm.
or over that particular function itself, it's just that function. For example, now the function over there is just x, and the derivative of that function is 1. So now if you have ln x, yeah, sure. Anytime in the form you have that derivative and that stuff, it's just the function of that, yeah, the ln of that function.
Yeah, exactly. So it's just 1 over x. You just got ln of x. So this is going to be ln of 1 minus ln of a.
Yes. Now we know that ln of 1 will be 0, yeah. Minus ln a. So the answer will just be minus ln a.
Okay, perfect. So we have
Or you
minus
can
ln of a. And now we need to know the limit. We want to take the limit as a goes to 0 of minus ln of a, right? Why do we need that? We want the entire area to the left in the first quadrant. So it's not good enough to just go to a. We need to take the actual limit as a goes to 0. And the reason that we have to do it with this limit process is if I just took a equals 0, I would get ln of 0. And ln of 0 is actually undefined because you can't solve the equation e to the x equals 0. Okay, there's no, let me in fact actually draw the graph of, if I draw the graph of y equals ln of x, what does it look like? It looks like this. This is the graph of y equals ln of x, right? So it turns out that you can only plug in positive numbers to ln of x. You can't plug in 0. But from this graph, we see what happens when a goes to 0, right? When a goes to 0, what does ln of a do? Well, it looks like the graph as you're going to 0, really, I should say this is a goes to 0 from the positive direction, right? We should be taking the limit as a goes to 0 from the positive direction of minus ln of a. Well, ln of a goes off to infinity as a is going to 0, right? So this is going to be, and in fact, ln of a doesn't just go to infinity. It looks like it goes off to negative infinity, right? So this is going to be negative infinity, or in other words, positive infinity. So we see again that the area here is infinite. Okay, so this, yeah, ln of a, ln of 0 basically goes to negative infinity. So when we take this limit, ln of a goes to negative infinity, which means negative ln of a goes to positive infinity. So this area here is actually infinite. If you look at the entire area under the graph to the left of x equals 1. Okay. All right, so this gives us infinite area over here. Okay, and it again comes from this logarithm function behaving in an interesting way. Okay, so we do it kind of the same way. We can't go directly from 0 to 1 because then you'd get ln of 0, which is undefined. But instead, you go from a to 1, you get ln of a, which is fine, or minus ln of a, which is fine. And then once you have that, you can take the limit as a goes to where you actually want, which is this 0. Okay? So this is what the area under the graph is between x equals 0 and x equals 1. Questions? Okay, let's do the next example. Similar thing, but now I'm going to have 1 divided by square root of x between x equals 0 and x equals 1. Point is, qualitatively, this graph looks exactly the same. Right? If I write 1 over square root of x, it's basically the same thing. Okay, this is y equals 1 over square root of x. It still goes off to infinity as x goes to 0, and it still goes down to 0 as x goes to infinity. So let's do the same thing. Here we have 1, here we have 0. We're looking to try to find this entire area. Well, I'll start with some a over here. So the area between x equals a and x equals 1 is, well, it's this area, this integral from a to 1 of 1 over square root of x dx. Let's rewrite that. Remember, 1 over square root of x is 1 over x to the 1/2 dx. And 1 over x to the 1/2 is the same thing as x to the negative 1/2 dx. Okay? And so now, so we have the integral from a to 1 of x to the minus 1/2 dx. So we know how to take an antiderivative of this because this is the power rule. It's just x raised to a number, and that number is not minus 1, so we don't need any logarithms or anything. We just have the power rule here. So we go, what you get is you have to raise the power by 1, so it's negative 1/2 plus 1, and then you divide it by negative 1/2 plus 1, evaluated from a to 1. And this simplifies. This is just x to the 1/2 times 1 over 1/2 from a to 1. And this is just 2x to the 1/2 evaluated from a to 1. And that's 2 times 1 to the 1/2 minus 2 times a to the 1/2. But raising to the 1/2 is just a square root. So this is just 2 minus 2 times square root of a. Okay, so the area between a and 1, when you take this antiderivative of x to the minus 1/2, you just get x to the 1/2 divided by 1/2, right? It's just the power rule. Raise the exponent by 1 and put it in the denominator. Okay, and when you simplify it all out, this comes out to be 2 minus 2 square root of a. So now we do what we did before. So let's take the limit as a goes to 0 from the positive end of 2 minus 2 square root of a. Well, this limit is much, much easier, right? You just say what happens as a goes to 0. Well, square root is continuous, so you just plug in a equals 0 for this limit. So that's 2 minus 2 square root of 0, and that's just equal to 2. Okay, so in this case, even though you have an area that goes on forever, you still have this asymptote here. This area still goes on forever, but basically the area gets skinny enough that the total area here is no longer infinite. The total area under this curve between 0 and 1 is actually equal to 2. Okay, so for 1 over x, you had an area equal to infinity, but for 1 over square root of x, it turns out that that kind of squishes the graph close enough to the y-axis that the total area underneath this part of the graph is just equal to 2 and not equal to infinity. Okay, and actually the computation for this is not so hard. All right, so any questions on this example, how we did it? So this just turns out to be 2. Okay. So let me give the general principle and then we'll finish. I'm not going to do one of these. What am I going to do? Yeah, I'm gonna skip slide 15. Okay, so this is what's called a type 2 integral. Yeah, so James, what you have is exactly right. So suppose that we have a function that's continuous on some interval from a to b, but maybe it's not continuous at b, right? This is exactly our situation, or our situation here, it was continuous on a to b, but maybe not at a, right? This function is continuous on the open interval from 0 to 1, but it's not continuous at 0, right? Because it has an asymptote. So if we have a function that's continuous from a to b, but maybe not at b, then how do we define the integral from a to b of f of x dx? Well, basically, we have to take a limit as t goes to b from the left side of the integral from a to t of f of x dx, if this limit exists. And likewise, what we saw here is that if f of x is continuous on the open interval from a to b, then how do we define the integral from a to b of f of x dx? We say that it's the limit as t goes to a from the positive side of the integral from t to b of f of x dx, right? We should think of this as here's b, here's a, and then we take t moving to a from the positive side. And in this case, we have here's a, here's b, and we think of t moving to b from the negative side. Okay, right? And in our example, we had, the integral from 0 to 1 of 1 over x dx. This was equal to, the limit. We'll use a different letter. The limit as t goes to 0 from the positive side of the integral from t to 1 of 1 over x dx. This is what we had in our example. Okay, so you want the area between 0 and 1, but it's not continuous, which means that you have to do this as a limit instead of doing it directly. And then same language that we use in the other case. If the limit exists, we say that the improper integral converges to the limit, and otherwise we say the improper integral diverges to the limit. Or is it just diverges? It's equal to infinity. Okay, so in the first case, it diverged because you got infinity. In the second case, it converged to 2. Okay, questions about this definition? There's nothing new here. Just saying that in order to evaluate these integrals where your function kind of blows up, becomes discontinuous, you want to understand an area, you have to do it by using a limit instead of just by doing it straight. Okay, so I'm going to skip this slide. It'll be in the notes. I'm just gonna skip it. So preview of next week. So why did we do all these improper integrals? What's the point of doing these integrals out to infinity or anything? Well, so there's many points, but one of the main reasons is that you want to understand these improper integrals when you study what's called continuous probability. Okay, and this is, as I mentioned at the beginning, this is how you make sense of probabilities when the outcomes can range over a continuous interval. So like, what will the temperature be tomorrow? And so in particular, you may have at some point seen a graph called the bell curve or the normal distribution. This is a graph that kind of looks like this. Okay, let me actually try to draw that a little bit more symmetric. Okay, this is called the bell curve. Okay, and it turns out that it models lots of natural phenomena. We'll talk more about it next week. And so we're going to see next week how probabilities like what are the chances that some normal random variable will take on a value at least 2 standard deviations above the mean? This is the kind of question that's asked all the time in experimental science. Like you have some expectation, but it has some variance, and you want to know what are the chances that that what actually happens could be very far away from your variance. It turns out that problem ends up being somehow about like measuring the area to the right of some line under this graph. Okay, this area turns out that it's going to represent a probability. Okay, so we'll talk more next week about how areas represent probabilities. And so these areas turn out to actually be computable by using improper integrals. The way you compute these areas is by taking integrals out to infinity of something going on. Okay, so we'll talk much more about it next week, but the whole point of doing this setup with improper integrals is to be able to talk about probability, which is an important application in any kind of statistics or experimental science. Okay, so we'll talk more. Today was the theory, was the math. Next week, we're going to talk more about the application for how to do this. Okay? So in the meantime, we have some exercises. These are a little challenging, so you can work on them. So the first one is evaluate the integral from 3 to infinity of x minus 2 to the negative 3 halves dx. And the question is, in order to do this, you need an antiderivative. You know how to find an antiderivative of x to the minus 3 halves. The question is, can you figure out, by guessing, let's say, an antiderivative for x minus 2 to the negative 3 halves? This is going to be one of these type 1 improper integrals. Second question, evaluate the integral from 0 to 5 of x plus 3 over x dx. This is what we call the type 2 improper integral. Remember that this is not continuous at x equals 0. Okay, so you're going to have to do this with a limit to x equals 0. And then the third question is, we've seen today that the integral from 1 to infinity of 1 over x squared dx converges. We showed that that was 1. What do you think about the integral from 1 to infinity of 1 over 2x squared plus 5 dx? So this is kind of a thought question. I don't expect you to be able to evaluate it, but see if you can reason about whether it converges or diverges. Is the area going to be infinite or is it going to be finite? So you can spend a little bit of time thinking about that. Okay? And then I'll say thank you for your attention. And so next week on April 17th, we'll discuss probability as an application of improper integrals. And we'll, of course, review all of this because this is an advanced concept and it's probably a little bit complicated when it's new to you about combining these limits with integration. So we'll definitely do a careful review of everything, and then we'll talk about how it relates to probability. Okay, great. So thank you for your time and attention as always. I wanted to ask, is Abraham is still here. Abraham, was there an announcement that you wanted to make?
The announcement is to all the math teachers in Lima, Ganta, especially Ganta, and also in Morovia. If you have interest into the competition for your school, please send the name of the students. Then we can be able to meet you to give you the test question, the questionnaire for you to go over it before the test. Because the test will be next month, by the 11th to the 15th. The test will be on.
Sorry,
so we'll ask all the math teachers into our class to be.
Sorry, Abraham, we lost you. Sorry, Abe?
Yeah.
Sorry, we lost you for a little bit.
So we want you people to send your name before the end of this month. Then we can be able to send it for to register the team. So any other questions?
So remember, if your school participates, it's 5 students. And I think we said no 12th graders because of the WAS.
Yeah.
The 10th and 11th graders.
Yeah, 10 and 11.
Yeah.
But we're having a problem with the 12th grader most of the time.
Okay.
Hello?
Yes. Hello?
Hello?
Hello, yeah. Yeah.
Like you said, next week, April 17th, we'll be discussing about probability in application of proper integrals. Or is there a specific topic that we'll be discussing? What if sometime we want to make a research before that time?
Yeah. So, I mean, we'll talk a lot about the normal distribution. So let me see if they have. So there is not. So I will say the probability application is not in the textbook. So what I would say you want to learn if you want to do a research is to research what's called the normal distribution.
Okay. No, I have something that even here we do that. That one is offered, the normal distribution is offered in math 305. They call it 305 at the Universal Library. It's also in it.
Okay, great.
Yeah, or you can also do the pausing distribution, a lot of stuff like that.
Okay, great. Yeah, so if there's anything you want to post about that to the chat room, please do.